This is homework from Muscles Day 3, in which I'm asking you to think through some problems about vertebrate smooth muscle and invertebrate smooth muscle. The first question was to sketch one motor unit of smooth muscle with 5 cells, but only 2 synapses. And the action potential should be able to start in one or more muscle cells and spread through them all. So we want one motor unit, meaning it's the muscle cells that are controlled by a single neuron. So when that neuron fires, they'll all contract. But we want only 2 synapses. So here's our 2 synapses, the only 2 places we're going to be releasing neurotransmitter. And action potentials from one need to spread to all the others, which means I'm going to need gap junctions, and I'll just show one. So remember, gap junctions are connexin proteins in each membrane. I'm drawing this little line in the middle because the connexins from one and the other, they meet and form an opening about 1 nanometer, big enough for amino acids and small molecules like that to go in. And my and I just realized I made a mistake here. I don't need this connection, so I'm going to replace it. And what I need is a connexin here and another connexin here. So an action potential will go down these two, and action potential will start here and go in all directions through this cell. It'll also allow sodium to go through into the neighboring cell and will spread an action potential through all of them. Action potential starts here, spreads in all directions from the synapse. Positive charge gets through the next cell, starts an action potential, spreads in all directions. And the action potential goes in all directions in this cell. Now, the next one wants one motor unit of vertebrate smooth muscle that has 3 smooth muscle cells. So 3 smooth muscle cells, each of which has at least one varicosity releasing neurotransmitter to the muscle cells. In this case, I'm going to want one or more axonal branches to go through the cell, and they're going to be varicosities. Varicosities just referring generically to bumps that show up on the axons. And if we zoomed in on one bump, what we'd see is something that looks like this with a whole bunch of neurotransmitter vesicles here. I'll just draw a few. The action potential would come through, and in this region, it would open voltage-gated calcium channels, allow calcium in. Calcium would bind to calcium binding protein, so here's a calcium binding protein, calcium. That would cause these vesicles to release neurotransmitter. So we'd have vesicles releasing neurotransmitter, and the neurotransmitter would bind to receptors, maybe ionotropic or metabotropic receptors that would result in opening sodium channels so that positive charge would flow into the muscle cells, and that could open calcium channels and allow calcium in. Or it could even be that a metabotropic receptor here activates cyclic MP to bind to calcium channels and open them up. So that will allow calcium to come into each cell. Okay, so in which of these, A or B, must it be possible for the muscle fibers to have action potentials, and in which should you not expect action potentials and just different amounts of sodium entry into the muscle cells, increasing with more neurotransmitter from the motor unit? So this one must have action potentials because it's the only way for the information to spread through the whole cell. And it's the only way to get an action potential in a neighboring cell. They have to have action potentials, and the cells have to be connected by gap junctions for this to work. In the second one, it actually wouldn't make sense to have gap junctions because the neurotransmitter release from each of these varicosities is allowing calcium in. With one action potential, we'd release just a few of these, but with more action potentials, we'd repeatedly release more and more neurotransmitter from the vesicles. We'd open more and more channels and have more and more calcium coming in. So the more neurotransmitter release, the more action potentials per second. The more neurotransmitter release, the stronger the contraction, because more calcium will come back to how later on. Show how myosin-regulated strengths of contraction would occur in the muscle fibers of both 1A and 1B above. Okay, so let's look at, here's one of the cells that produces action potentials. And so here was the neurotransmitter release coming in here, and we're going to get action potentials going in all directions. What that is going to cause at every location is going to cause opening of voltage-gated calcium channels, calcium entry into the cell, calcium binding to a calcium binding protein, in this case calmodulin, that binding to myosin light chain kinase, MLCK, myosin light chain kinase, then each time it gets near to a myosin head, the myosin light chain is right here. So the myosin heavy chain is this. This is a long stem on the myosin, and the myosin light chain is just this little piece on the neck here. So myosin light chain kinase then takes an ATP. You end up with an ADP and a covalently bound phosphate. So over time, each one of these you activate can over time activate more and more myosin heads. And as each myosin head is activated, it can start moving a chain of actins and start contraction. Okay, so with more action potentials per second, we get more calcium in, more activated myosin light chain kinase, and we're going to accumulate more and more myosin heads that are phosphorylated. And contraction will continue until a phosphatase comes along and cuts off that phosphate. So let's look at the other one. The other one from 1B had varicosities at various places that were releasing neurotransmitter. So we have multiple locations where a neurotransmitter is being released. At each of those locations, we're either going to use an ionotropic receptor that maybe lets sodium in, and that opens voltage-gated calcium channels, and we can have exactly the same pathway. Or we could have it be a metabotropic receptor, but again, letting calcium in and doing the same pathway. So in both cases, we're using myosin regulated. We're phosphorylating myosin. This is, remember, not the location where ATP binds, and this is a covalently bound phosphate. ATP binds at another site on the myosin head and the myosin heavy chain. B, how would different numbers of action potentials per second in 1A and 1B cause different strengths of contraction in the muscle? So in this case, each action potential opens or reopens calcium channels, activates more myosin light chain kinase, and you get more myosin heads activated. So a single action potential might just get a few of them, and you'd have a very weak contraction. Most of the myosins would do nothing. More action potentials per second, you get more calcium, more MLCK, and you might activate every single one with enough action potentials and have a full strength contraction. Here, each action potential releases a little more neurotransmitter at each site, but again, each action potential gets you a little bit more calcium and more myosin light chain kinase. So now we want a muscle that is a flexor at one joint of the finger. So here's the muscle. Here is the bone. And other bone. We're going to attach it at both ends with a tendon. And the muscle should have 4 muscle cells and 2 motor units. So here's 1, 2, 3, 4. And I will do motor unit 1 and a branch over here. And motor unit 2 and a second axonal branch there. So now we have 1 muscle with 4 muscle cells, 2 motor units. And would action potential spread from one motor unit to the other? So the question here is, if we had action potentials here, would those action potentials spread to these neighboring ones? And the answer is no. Each muscle cell in this, or muscle fiber, same thing as a muscle cell, it's electrically separated. So the action potential in here goes through this cell and nowhere else. And the action potential here through that cell and nowhere else. So if only motor neuron 1 is firing, then only these 2 cells will contract. If motor neuron 2 is firing, only these 2 will contract. Will this muscle have nearly infinitely many different strengths of contraction, or just a few different contraction strengths? So this one will have, if we only fire M1, we get 50% strength. These 2 cells, M2, also 50% strength. M1 and 2, we get full strength. Okay, because each action potential in a skeletal muscle cell is going to, instead of myosin regulated, remember it's actin regulated, it's going to release enough calcium into that cell to activate every myosin and actin. We get a full strength contraction, or close to it, and full strength. As sketched, is it possible to have the cells in muscle FM, this is muscle FM, to all contract at the same time? Not as I've shown it so far, because we've got 2 separate motor units. But if we add to it a neural circuit that will cause the entire muscle to contract at the same time, this will do it. This interneuron up at the top, if that fires, will cause the entire muscle to contract, and we'll get a full strength contraction. If we only have 1 action potential from here, the muscle will contract, but that's going to be really fast. This is the contraction is going to last for a fraction of a second. The whole muscle won't shorten very much. It'll be full strength while it goes, but it won't shorten very much, and it's just called a twitch. If we continue those action potentials, the muscle will continue to contract over time, and it will shorten a lot more and bring these finger bones together. Here it's add to the muscle 2 sensory neurons, and we want SX to increase action potentials only if the muscle shortens, SY if the muscle is under tension, in other words, trying to lift something very heavy. So I'm going to have sensory neuron FX. It's only going to fire action potentials out to some target if the muscle shortens. So I'm going to wrap a dendrite in between these muscle cells and put in stretch channels such that when this muscle shortens, it's going to put strain on these stretch channels, and we'll get action potentials in S1. What about tension? Well, the tension is built up at the ends to pull those bones together. So for S2, I want a sensory neuron that has stretch channels in the tendon, maybe at both ends, but I'll just draw it on the one end. And this one, S2, will produce action potentials when this is under tension. Notice we don't have to shorten this muscle to be under tension. We could have something that's impossible to move at the tip of the finger, be contracting as hard as possible, getting these trying to contract, but being just as long as ever, so they're not putting pressure on this, but that tension will be squeezing against the fibers and the stretch channels in here. That'll cause action potentials in S2, but not S1. On the other hand, if we shorten this with no load, that'll create almost no tension, 0 or no action potentials in S2, but when the muscle gets shorter and fatter, that's going to cause a lot of action potentials in S1. So S1 is detecting how short the muscle is. You use that to tell the position of muscles and arms and legs in your body. And S2 is telling the tension. So that's 5A. 5B, propose a number of action potentials per second in SX when the muscle is completely relaxed, shortened to 1/2 its maximum shortening, and shortened to its maximum possible. So we might decide that 0 or maybe a few action potentials per second in SX. When not shortened, when it's completely relaxed, shortened to 1/2 its maximum shortening, maybe 50 action potentials at 50% of its maximum, and 100 action potentials per second at 100%. That's as short as it can get, as contracted as it can get. Or if you know a bit more about neurobiology, you might realize that even when relaxed, a lot of sensory neurons are producing a few action potentials, so we could go with 10, 60, 110. And these would be reasonable ranges for a sensory neuron. This is a little on the high side for how fast a typical sensory neuron can produce action potentials. So what about SY? So here's SY, no tension, 0 action potentials per second, 50% of maximum tension or moderate tension. Maybe that would be 50, and at maximum tension around the point where you're about to tear that ligament, you might have 100 action potentials per second. Okay, in the muscle FM, is it possible to have low numbers of action potentials per second in SX, but maximum in SY, and the reverse? So let's look back. So could we get low numbers of action potentials in SX, I think this was, and this was SY. Could we get low numbers of action potentials in here, or sorry, high numbers in SX, and low numbers here? And you could, if you shorten, but there's almost no tension, you're not putting any pressure on here. In other words, you're moving your finger, but it's not pushing or pulling against anything. You'd have many action potentials per second because the muscle is shorter, but not here. On the other hand, if you're pulling your finger against something that won't move, pulling against a heavy weight, this may be working really hard, but it's not shorter, and so you get few action potentials per second in S1. This may be under a lot of tension, and so you get many action potentials per second in S2 or SY. Finally, propose reasons, ultimate causes, so evolutionarily, why might it make sense, for many small invertebrates to control entire muscles with only one motor unit. One motor unit with just 2 neurons, and we could have as many muscles as we wanted here, but one of these, oops, make it red, one of these is inhibitory, and the other is excitatory. So why might that be? Whereas you are controlling your major skeletal muscles like your biceps or your major leg muscles with thousands of motor units and thousands of motor neurons, one for each motor unit. So if you're large, you would have, even with our very large skeletal muscle cells, you have a lot of different neurons because you have to reach every single muscle cell with an axon terminal. And because you have thousands of motor units, because you have thousands of cells or even tens of thousands or more of cells in those big muscles, you can have 1,000 different strengths of contraction just by having 1, 2, 3, 4, 5, all the way up to 1,000 different strengths of contraction. This would be just one set of muscle fibers, 1/1,000th, so little you'd barely notice. 2, 3, all up to full strength, all of them contracting as strongly as possible. Gives you a lot of variation of strength for when you're picking up really heavy weights to when you're delicately picking up one tiny little thing. On the other hand, an insect is very small. It may have muscles that only have a few muscle cells, and every neuron may be expensive. In small insects, they may not have all that many neurons, plus neurons are expensive tissue, all those action potentials. So a small insect may be able to control a single muscle using myosin-regulated. Remember, with myosin-regulated muscle, it doesn't matter that we only have one excitatory neuron here, because if we just have a few action potentials, or 1 per second, we're only going to activate a few myosin heads. And so if only 1 out of 1,000 myosin heads is activated, you'll have a 1,000th strength contraction. And it'll happen in every cell. If you fire more action potentials per second, you can get more and more calcium in, more and more myosin light chain kinase, and so you can gradually work up to having a full strength contraction. The advantage of this is that it takes only one neuron to control the whole muscle, and so all your neural circuits only need to go down to one neuron. In a major skeletal muscle in you have neural circuits where you have to have the inner neurons going to 100, 1,000 different motor units. That's a lot more complicated. It's a lot more tissue. It's a lot more expensive. You can afford it because you're big and you've got a lot of cells. But for a small insect, the complexity adds costs, and so it's cheaper to do it this way. The disadvantage is that your skeletal muscles are much faster. The myosin-regulated movement in an insect is going to happen more slowly. On the other hand, a small insect gains so much by the efficiency that the speed may not matter. And in addition to that, the time delay is not as critical for a really small animal because it doesn't have as much inertia to get moving. Large animals have a lot more inertia to get moving. They can't change direction and shift as much. And so the selection favoring faster speed may be more intense. And then why an inhibitory neuron? Well, it's very handy to be able to turn things off. So this inhibitory neuron can start turning off, in other words, activating phosphatases to turn off the myosin, to remove the phosphates from the myosin heads and inactivate them. And it means it's easy to cause some action, but correctly, when needed, to have an opposing muscle activate the inhibitory neuron and stop the contraction. So commonly 1 excitatory, 1 inhibitory, or sometimes 2 excitatory and 2 inhibitory, giving fairly fine control, but not quite as fast contraction because it takes time to activate those heads.